Right. Welcome everyone to the 74th meeting of New Directions in Group Theory and Triangulated Categories. This will be our last talk of this season before we break for summer. Today our speaker is Amalendu Krishna from the Indian Institute of Science, and he will be talking to us about ramified class field theory of curves over local fields.
Okay, so thank you, Raghudeep, for inviting me to give this talk. Let me begin now. So let's see. So what happened? Yeah. So this is for class field theory for curves over local fields. This is joint work with Subhadip Majumder. Okay. So, right. So, what is the aim of this talk? Is to establish some class field theory for smooth curves over local field. So recall that what is a local field?
Hi, I think, is there some kind of noise in the background, or am I?
I don't see any noise. Did you get some noise still?
Yeah. No? Okay, ignore me. No, it's fine. It's fine, ignore me.
Okay, so right. So what's a local field? It's basically a complete discrete evaluation field with finite residue field. Right. So, for example, in characteristic 0, it could be like QP or some finite extension of QP. Or something like in characteristic P, it could be FQ and something like this. Right. So before I discuss this class field theory for curves over such fields, let me just give a so recall that what happens over finite fields. So basically, over finite fields, CFT is kind of well established, is well understood. So right. So what is the main theorem basically in this case? So main theorem basically this theorem is already due to, I think, Sayre, and before Sayre for by other people, Artin and Lang and so on, for smooth projective curves. So this says the following. So let X be a smooth curve over a finite field. So then there exists a reciprocity homomorphism which I denote as rho X from is something called the class group of X to the étale fundamental group, the abelianized étale fundamental group of X. So the classical theory, if you recall, basically tries to describe the étale fundamental group of varieties or the function fields of varieties in terms of certain motivic gadgets like this class group. So this motivic object should be an invariant of X, and it should be completely defined in terms of X. Recall that étale fundamental group of a variety is not defined intrinsically in terms of X. This describes the coverings. So this is some kind of outer invariant of X. To define this, you need to kind of go out of X. So that's why it's very hard to compute this, because you have to take care of all possible coverings. But the idea is to sort of replace this by something which is much easier and you can directly understand in terms of X. And a question remains that how much this side captures the other side. And that is what the goal of classical theory is. Right. So homomorphism such that there exists exact sequence 0 to C of X to phi 1 abelian of X to Z hat mod Z to 0. So as you see that in this case, classical theory is basically completely understood, and it says that the fundamental group of a smooth curve is indeed you can describe in terms of, and let me just also tell you that what is this Cx. So basically Cx is something like co-kernel of the map from K1 of the function field of K. So here let's write K is the function field of X to direct sum over X. So let's do the following. Let's fix. Remember that any smooth curve over finite field has a smooth compactification. So I fix this. What happened? I don't know. Right. I suddenly went off. Okay, so where I was. Yeah. Okay, so I think something wrong happened. Yes, it's here. Okay, so right. So so you choose. Oh my God! You just went back to its original position. Right. So X bar. So then you take X into X, and you take Z, and also you. What about other points? You take X not in X. Here you take K1 of K of X. So these are all like Milner K theory of K groups of points. This is K naught, this is K1. And remember that from here to you have this boundary map, and from here to this should be, I made a mistake. This should be something like you look at, okay, this should be not K of X. This should be, you look at local ring at X, and you take its Henselization, and then you take its function field, the quotient field of that. So then you have the inclusion of K into this function field, and that gives you a map on K1. So this is this map, and this is the first is the boundary map. Take the co-kernel, and right. So you can. So this is right. So basically, you can see that This is also the motivic cohomology with compact support, something like H2C of X Z1. Right. So this is what we know about the class field theory. And so, so basically here you see that there is this extra factor, this guy. So this guy basically describes those covers of X, finite abelian covers in which all closed points are actually totally split. So they are not really so interesting. So the main part of this is actually described by the class. That's the point. Right. So now what happens over now over local fields? So fix a local field K and X a smooth projective curve over K. Right. And let's choose some X naught open in X. And I can let's choose this to be open affine, because otherwise I just take X itself. So whenever I write X naught, I don't assume this to be X itself. Okay. Actually, for the theory, it doesn't matter whether it's X naught or X. Okay. So right. So in this case, what is known? Let me first describe what is known in this case. So in this case, what we can say is the following. So there is a works by Saito, Suji Saito, and Kato and Saito together, and also by someone called Yoshida. So if you combine this, they proved independent results, all three authors. And if you combine all of them, what comes out is the following. So here is the theorem. This is the following. So there exists a reciprocity, homomorphism, rho x from C of x to C of x. Remember, this x is a smooth projective. So without loss of generality, you can assume x is connected. So I will always assume that. So you have this reciprocity homomorphism. So what is this Cx here? This Cx is not same as the other one. So this is co-kernel of the map from, now instead of K1 here, I take K2. And then you have the boundary map to K1 of all the closed points in X, right? And you have this boundary map in K theory. For example, if you write the Guston sequence and take the co-kernel of this, and this is called the class group, and you can check that this is actually a motivic object. Actually, it is nothing but, if you know higher Chow groups, this is just CS2 x comma 1. And it has a block formula, so it is also equal to H1. You can take Jareski or Nisnevich x K2 of x. So you see, indeed, a motivic object defined by cycles. So basically, whenever I say motivic, for me, it will always mean something defined in terms of algebraic cycles, right? And there is a such homomorphism. And what does it do? So it satisfies the following property. So one, that first of all, actually it is known that in this case, unlike in case of finite field, rho x may not be injective actually. So, but then you can say that what is the kernel? So basically, their theorem is the kernel is divisible. You may recall that a profinite group cannot contain a divisible group. So if there is a divisible subgroup of Cx, it must die under rho x. And the point is that this is the only thing which can die. That's what this theorem is saying. That whatever which has to die, that is the only thing which dies under rho x. Nothing else dies. That's what part 1 says. And second thing which says is that if you look at the image of Cx naught, so what is Cx naught? Let me recall here that remember that Cx, and from here you have a push forward map to K star, right? Which is nothing but in terms of cycles, this is Ch1 K comma 1. So you have this push forward map, and you just look at the kernel of this, which I call the degree 0 algebraic cycles. Right, so this is degree 0 class group, and the point is that the image of this under rho x is finite. Right, and the third thing which they show is that if you look at the co-kernel of rho x and take it in the degree 0 part, then this is isomorphic to z hat to the power r. So degree 0 means, remember that you have a map from, let me write here, Cx to Cx, and this, and then similarly you have here pi 1 abelian of x, and here you have pi 1 abelian x degree 0. What is this? This is the kernel of the map from pi 1 abelian x to pi 1 abelian of point, which is just the Galois group of abelianary Galois group of the base field. And this is what I call rho x0. Right, and what the theorem says that co-kernel is just this. What is R here? So R is something, some geometric object. Basically, you look at the Albanese variety of X, and it has a neuron model. And neuron model may not have good reduction, but it has always semi-stable reduction. So the special fiber may be semi-abelian variety, and so it has the maximal torus, and R is the rank of that maximal torus. Sometimes it's called also the rank of X. So as you see that this theorem says that, well, this is the best you can do over local fields. It's slightly not as nice as in the case of finite field, but still is very good because it does capture, the class group does capture a lot of information about the étale fundamental group of X. Right. Now, the question is the following. Remember that here the X is projected. But what I am interested in is a case when X is, what if X is not projected? Right. This is the case I am interested in. So in this case, the following is known. We know the following. So what do we know? This is a theorem by someone called Hiranuchi, which says the following, that there exists a reciprocity homomorphism rho x from Cx. Remember, my x naught is a fine curve, to pi 1 abelian of x naught. And well, how do you define Cx naught? So one way is that you can take Cx naught to be Mottevich cohomology of X with compact support. Right? You can take that. And this is also some kind of algebraic cycles. This is defined by algebraic cycles. For example, you could think of this as some kind of higher version of Suslin homology. So more concretely, you can check that this is actually the co-kernel of K2 of K2. Here is look at X in X naught, K X star, and direct sum here X naught in X naught. If again, now you look like K2 of, again, like before, the Henselization at X, and look at the co-kernel. So one can check that this motivic cohomology with compact support is actually just this. So, right, and clearly there is a surjection from here to here, as you can expect, because the motivic cohomology with compact support maps to the compact support cohomology of the compactification. And this is right. And Hiranouchi constructed reciprocity from here to here. And what does it prove? So it proves the following, that rho x satisfies the following. He says that, right. So, so what does he say? He says that, let me see. So, yeah. He says that one, that kernel of rho x naught is divisible by all primes different from characteristic of K. That's what he says. And second thing he says that if you look at the topological co-kernel, not the actual co-kernel. So what's topological co-kernel? Remember that this fundamental group is a profinite group. It's a profinite topology. So you look at the co-kernel of the degree 0 map, rho x0. So look at this degree 0 map, and you take its image and take its closure in the profinite topology, and then take the quotient. That's a topological co-kernel. He says that this is also isomorphic to ZR to the power R, which R is the same R in which we had in the previous theorem. So this is what he says. So this theorem is not completely. It's not. It doesn't give every information. Not as good as the theorem in the case of projective case. Why? First of all, as you see, one says that it's divisible only by primes or numbers, integers different from the characteristics. It does not tell you what happens, whether this rho x0 is completely divisible. We don't know that. Secondly, it says that only the topological co-kernel is of this type. And it doesn't say what happens to the image or any such thing. So, so we have some theorem, but it's not completely optimal. Right. So then the question remains that there are several questions that which still remain. Are the following. First, that is rho x0 divisible. That's the open question, in fact, for a very long time now. And secondly, is image rho x0 in degree 0 finite? Remember, all these things are true for projective case, right? And third, does rho x0 describe the class field theory? In other words, describe all finite abelian covers abelian covers of x naught. Right? This is what you want. Like you want to somehow describe all finite abelian covers in terms of class group. So, this, and I will explain this more. And this is a very interesting question because it has a lot of arithmetic implications. Like, so these are the questions which still remain, and they are all answers of all these questions are, as we saw, affirmative for projective case. So, so what I will do today is basically try to answer all three questions in affirmative, actually. So that's the main result which I want to describe. So main results today. Right. So what are the main results? So so let x naught be as above. Right. So let's assume that characteristic of K is positive. Why? Because by Hiranouchi's theorem, if characteristic of K is 0, then we know that its kernel is divisible, right? Because he only thing he leaves is the characteristic. So basically, the if you have seen a little bit of class field theory, the main problem is this p-adic part, the p part of class field theory and characteristic P, which creates lots of problem, right? So this is always the case, that the p part always creates problem, right? So same is the problem here. So now so let's assume the characteristic of the p is K is positive, and let's say p is the characteristic. So so and rho x is also as above. Then what we prove is the following. So in order to prove this theorem, we generalize this whole question. So we generalize the question itself. So what we do is that we fix a divisor, which if you see Sayre's class field theory and book, algebraic group in class field theory, then he calls something called, he fix a, what do you call, the modulus. What is a modular? It's an effective divisor, let's say D, such that the support of D, we'll write like this, is exactly equal to x minus x naught. Right, so you fix some, you look at the complement of x naught in X, and you just put some some thickening, take some thickening of that, any arbitrary thickening of that closed subset, and that's your effective divisor is supported on this complement. That is called the modulus. And the question is that so what this modulus does is, to be more, if you want to understand geometrically, what it does is that, if you remember, if you want to study, so you have this x naught here, you have x here, and remember that you are interested in understanding finite abelian covers of this. Now, if you have any such let's say finite map, finite abelian cover, étale cover, then clearly it extends to a map from y to x. That's obvious. That's very easy to do. Just take the normalization of x, y naught closure in the function field of y naught, and it maps. But the problem is that this may not be an étale cover, but it may have ramification. Now it may have very, very bad ramification outside x naught. So that is because of this basically this ramification problem. It's very difficult to study these kind of covers. So what you do is that you fix some modulus here, and what this modulus does is it allows you to understand these coverings where this cover y to x, which may not be étale, it may have ramification, but the ramification is kind of bounded by something this D. So it has some kind of fixed finite level of ramification, and that allows you to study, it makes things much easier to basically study these kind of coverings. And that's the basically goal of fixing this divisor D. So you may be wondering that why I fix this divisor. Basically, I want to sort of control the ramification of these y's outside X naught. Right. So fix the modulus divisor D, and then we can define what you call the class group with modulus. Which we write as CXD. So how do you define this? This is also some kind of, you may think of this kind of relative sort of motivic cohomology of X related to D. So one way to define this, you look at the co-kernel of K2 of K2. Again, this part is same with KX star, where X is in X naught. Right. But here what I do is that I take direct sum X in D. Here I take K2 of Kx as the Henselization, but mod out by something called some fill D of K2 of KHX. So this fill D is some subgroup of K2 of Kx, which takes basically, which is of the form something like 1 plus mx nx tensor kxh star, where mx is the maximal ideal of the local ring, the discrete value-based ring at x, and nx is the coefficient of this d, thickening of d at x, and then you map it to K2 of KXS. So take the image, and this is what this thing is, right? So then if you do the co-kernel, you get this thing. If you recall, if I don't take this part, then exactly I get CX naught. If I don't take the whole this part, I get CX. So basically, in other words, you get then CX naught mapping to CXD, and then this mapping to CX. And it turns out that, right, so these are the maps. And the idea is to understand this in terms of taking some limit of this, keep increasing the thickening of D and take the limit, and hope is that you should get this kind of thing. So that's why you fix some modulus and then do some limit argument. Right. So the theorem is basically, the first theorem one is the following. That there exists a reciprocity rho xd from cxd to something called pi 1 abelian xd. So this is basically some kind of fundamental group of, from this case, some fundamental group which describes abelian covers of x naught, which have ramification bounded by D outside X naught. So this is basically you can define some kind of Galois category of this kind of covers. And if you take the fiber functor of that Galois category and take the automorphism group, you get this group and take the abelianization. Right. So which satisfies the following. So which satisfies the following. One, first thing that if you look at this map rho xd and mod n to pi 1 abelian xd mod n, then the theorem is that this is injective for every integer n, including n which is divisible by p. Two, if you look at n torsion of cx of d, to n torsion of pi 1 abelian x comma d. No, I think this I should not say right now. So This I should not say right now. Right. Right. So right. So but the second thing is that I should say is that kernel of row x t is divisible. Right. And 3, actually the image of row x d and degree 0 here we may not actually be finite. Right. And the 4 says exactly the class field theory, that there exists exact sequence 0 to q mod z raised to r to pi 1 abelian x d dual to cxd dual, and take the torsion of that 0. So if you understand actually this exact sequence, what it does, it exactly tells you that there is a one-to-one correspondence between all finite abelian cover of x naught with ramification bounded by d, and where not all points of x naught are completely split, are described in one-to-one correspondence with all open subgroup of cxd which have finite index. So actually CXD, you can define some topology also, which I did not describe. Right, so the theorem 2 says that there exists reciprocity. Now I am going to x naught, you see, pi 1 abelian x naught, which satisfies, again, same 1 to 4 as above. Right. So yes. So yeah. So now you see that okay. So now you see that this completely answers basically all the questions which I had raised. So remember that we wanted to know whether the kernel of rho xd or rho x naught is divisible or not, and we say that it's actually divisible. In fact, we say more than that, in the sense that we say that if you take with finite coefficient, then actually the reciprocity map is injected. So this is just like what happens in the projective case. But remember, in the projective case, we had the theorem that it says that image is always finite. But here, actually, this is not the case. It may not be finite. Right. In fact, in almost all affine case, this will not be finite. Right. Is there any question? Okay, so right, so these are basically this answers all the things which you wanted to know about class field theory of curves. Now, so I just remark one thing, that why is this theorem important? This theorem because basically it tells you one thing, that so you remember that now you have. You can do you can ask a lot of questions now. Suppose you take Cx naught and you take pi 1 abelian of x naught. Now, you may find many open subgroup, right? You may find many open subgroup of this, let's call it U. Now, this theorem says that corresponding open subgroup of finite index, this theorem says that, well, there exists a finite abelian cover actually of x naught. Let's call it y naught, right? Which has some ramification, whatever. Now you may ask that, well, what is this y naught? How do you get it? On the other side, suppose you somehow you have this x naught, and you know you have some finite abelian cover. Suppose you can cook up some finite abelian cover. Then you can ask that, well, what subgroup of this class group it gives rise to? In other words, that if I have a finite abelian cover, there should be some cycles on X0, which should describe these abelian covers. Can you find out what that cycle is? And that is a very challenging question and very interesting question. So basically, what this theorem tells you that not only for projective case, sometimes, in fact, quite often, you need to sort of, given these kind of coverings of open affines, because there aren't too many affine curves. Now the question is that if you know these affine curves, can you describe them in terms of cycles? What cycle do you get? If you have some fixed curves, covers, can you find some cycles? And that's very interesting from cycle point of view, particularly for people who study algebraic cycles. It's a big curiosity to find such cycles, right? So that is, in that sense, this theorem is very important because it sort of gives you some homework to do some work, and it has I don't want to say right now, but it has a lot of arithmetic implications, right? So now the question is how to prove this theorem, these results. Well, there are basically there are two main steps. So one is to prove a class field theory for two local fields. What is two local fields? Two local fields means complete local field, complete discrete valuation fields whose residue fields are actually one local fields, like local fields as above. Right. And second, a duality theorem for p-adic et al. Cohomology. So see that for prime to p coefficients, particularly over separably closed field, we have this Poincare duality, right, for et al. Cohomology. But it is not clear what is the meaning of p-adic et al. Cohomology, and can you prove some duality for that? So this itself is a very challenging kind of question in arithmetic geometry, to sort of have appropriate notion of p-adic cohomology and prove some kind of Poincare duality for them. It's a very non-trivial problem. So we prove some duality, which is enough for our purposes, right? So let's do first CFT for two local fields. So so let K be a two local field, which means, as I said before, it's a discrete valuation field whose residue field is a local field. Then Kato defined a reciprocity homomorphism rho K from K2 of K to the abelianized Galois group of K. And in fact, Kato defined a topology on K2 of K and says that, and this is a profinite topology, that this map is continuous. Right. So, and what Kato proved, so moreover, we know the following about this map. One, he says that the image of rho K is dense. Two, he says that if you look at the map on dual, so that means that if you take, remember that the dual of Galois group is the H1 of K Q mod Z. And you look at the K2, K, remember it has some topology called Kato topology. Look at the dual of this, whereby dual means look at all continuous homomorphism from K2 of K to Q mod G, where Q mod G are discrete topology. And then he proved that this is bisected. Right. And then the third thing is, which is not by Kato, but it is by Fesenko. What Fesenko proved is that the kernel of rho K is actually divisible. It's a very non-trivial theorem of Fesenko. It's not so easy to prove. Right. So this is what we know about this reciprocity for two local fields. But there are many things we still don't know about this. And what we do is that we prove some new results in this CFT for local field. So our some new results. So what we prove is the following. So this is theorem 3. We saw that, if you look at this reciprocity for K2 of K mod N to Galois group mod N, then we saw that this is injective for every N. This is 1. 2, we saw that if you look at the N torsion in K2 of K to N torsion in the Galois group of K, I will not write the abelian, but it just means always abelian for us. This is surjective for every N. Right. So these are the two new results basically, which does not follow from those 3 results. In fact, on the other hand, a corollary of 1 and 2 is that theorem 3 implies Fesenko's theorem. So it gives a very simple proof of Fesenko's theorem that kernel is divisible, because the point is that the Galois group has no specifically P torsion. So if you use that and use these two second for part 1 and part 2, it very immediately you get that the kernel is divisible. Right. So so in fact, we also saw that basically the co-kernel is also torsion free of reciprocity, and it is divisible by all prime different from the characteristic of K, but it's not divisible by P. P is the characteristic. Right. So let's assume that here I am assuming again that the characteristic of K is equal to P is bigger than 0. Right. So this is the new basically results in the class field theory of two-dimensional local fields, which were not known before. Right. And right. So what is the by the way, I should also tell you that this K2 of K to G Galois group, this map is actually kernel may be non-zero. It's known that the kernel is non-zero, and it's not hard to prove. Not hard to prove that this is the case. Right, and now let me go to the duality part. So this is basically, I don't have much time, so I will just keep it very short. So Kato and Saito, I just give you very brief review of what duality we proved. They proved that if X, okay, so why should I write if X? I have already said X is projective, right? So there exists a perfect duality like this. You look at hi of x wm omega 2 of x log. This is, what is this? This is like, if you know Dirac bit, this is just the logarithmic Dirac bit forms. And here you have h2 minus, and this is et al cohomology of x z mod pm to z mod pm for every I. So it is kind of understood that these guys define the p-adic et al cohomology of smooth varieties, at least for projective varieties. They do give you a theory of p-adic et al cohomology. So you get some kind of Poincare duality for p-adic cohomology. Now, what happens if you have a modulus divisor D? Can you prove some relative sort of duality? So what the theorem we prove is the following. Theorem says that there exists a perfect duality. Namely, you look at hi of x is all et al. Something called relative log Dirac bit form with respect to D. Is kind of, you can think of this as a relative p-adic cohomology, which I refrain from defining because it was a little bit technical. Times h2 minus I et al of x, and it's very similar to that z mod pm, but some kind of relative version of z mod pm, which is called x mod d. So it cannot be z mod pm if you think about it, but it's some twisted version of z mod pm on. So it's a kind of relative z mod pm you could think of. Z mod pm. Right. So this is what. So if you compare this, what we do is that we prove a new duality theorem in the setting of modulus. And why it is interesting, you may say, well, the point is that if you take the limit of this as d varies, thickening varies, if you take the limit, then this becomes h2 minus I et al of x naught z mod pm. Right. And if you take here projective limit, this is inductive limit. If you take projective limit, you get some cohomology of x naught. Some limit, let's write here something, to z mod p. So in other words, you get, so this limit is actually called the p-adic et al cohomology of x naught with compact support. And this is also p-adic et al cohomology of x naught with compact support. This is actually the p-adic cohomology of x naught, not with compact support. So remember that if you know cohomology theory, you know that for non-projective variety, there should be a duality between cohomology with compact support and actual cohomology. If you stereotype it, that's what I am trying to write here. There is a perfect duality between motivic cohomology, et al motivic cohomology with compact support, and actual motivic cohomology of x naught. So we get this duality as a corollary. So that's why this is interesting, that this allows you to deduce this duality. It's not easy to directly deduce this. Right. So so map goes like this. And this is identity. Right. So basically, this generalizes that duality theorem of Kato and Saito. Now, I don't have much time, so I have like 2-3 minutes. So let me just tell you how to prove at least something. So some proof. Right. So I have just stated many results, but let me just give you one proof that how these things imply one of the main things. So let's prove that y cxd mod n to pi 1 abelian xd mod n is injected. Well, Yeah. So proof. Well, if P does not divide N, then this is easy. This is not difficult. It just follows from some duality theorem et al. Cohomology, and plus one extra input it uses is what is called block-Kato conjecture. Once you combine block-Kato conjecture with some duality, you get it. So that's not the main point. The main point is what happens when P divides N. And that's the hard part. So we assume that, we assume that N is, let's say, some P power. Right. Now, how do you do it? Well, so let me just quickly say this. So now you see what happens. So here you have CXD mod PM. Now, you remember this, we can show that this is some kind of a Nishnevich cohomology, right? This is, remember, this algebraic cycle is some kind of relative Chow group. This should be X, K, some kind of M, X mod D, some relative K2, some relative K2. And you can do the same thing, but instead of Nishnevich et al., I can take et al. So I write here et al. Of X mod D, et al. Cohomology. I have the realization map. Now what happens is that from here, you can construct, remember that there is a duality, right? Duality theorem tells you that there is a map from here to what is called H1X G mod PM, this XD. Remember this XD dual, right? And this sits inside CT et al. X PM. I should make correction here. So actually, I should not tell you that this theorem, the way it is stated, is not quite correct. In fact, it's incorrect. Actually, the point is that this has some topology which we define. It's much more subtle than what I wrote. So I have to define a topology here, which is very difficult to do, but we do that. And then I take some profinite completion. Otherwise, we can show that without that, this duality is never true, actually always fair. And you may wonder that there is no such thing here, but point is that we show that the topology we give here, if D is empty, then this is already profinite. So even if you put here PF, it makes no difference. Right? PF is the profinite completion of this some topological ability group. So then you can take the profinite completion here. There will be no such thing. Profinite completion of the whole thing. And mod P. Whatever. And then you have this duality map. This is a duality theorem. And duality theorem says that this is bijection, right? That's what duality theorem said. So, yeah. And it's not hard to show that this map from Cx comma D to its profinite completion is injective. In other words, this topology which we give here is Hausdorff. These steps are not trivial, but one has to prove that why this is Hausdorff. And once you know this is Hausdorff, it's not hard to show this is injective. So, so basically that means that this map is injective because it's a composition. And then it's not hard to show that the one step is there, one more step, that this is injective. And we saw that finally, that this composition is exactly my rho XD. And we also saw that another thing we have to show that this is actually pi 1 abelian XD mod PM. So there are several steps. One is that you have to show this, which is not very hard. And then this you have to do some work. This is one of the hardest part, and this is not very hard. And then you just trace this diagram. All maps are injective. It follows that this is injective. So this implies that rho XD mod P to the power M is injective. And if you take X naught, basically you can do the same kind of argument. Argument is very similar like this by using some kind of this duality. So I think I have already basically taken more time than I had. So I'm sorry about it, and I think I should stop. If you have any question, you can ask.
Thank you, Amalendu. Can we all unmute ourselves and give the speaker a round of applause? Okay, if you have any questions, you can ask them now. So I had a question. So can you go back to this corollary that implied Fesenko's theorem? You had this. Yeah. So when the characteristic of K is 0, is it trivial?
Yes, because in that case, again, you can use the Mercury-Suslin theorem, and you can go from K2 of K mod n to the corresponding étale cohomology mod n, and then this is also, Galois group is also a dual of the étale cohomology, and then you use the duality, and plus then basically it just follows from duality and Mercury-Suslin theorem. That this happens. In fact, in that case, it's an isomorphism mod n.
And that is known already, I'm guessing.
Yeah, that's already known that if n is prime to p, there is not the problem. The problem is n is not prime to p. That's the main problem here. Right.
Okay.
But I should tell you that in this part second, actually opposite happens. If you take p towards n, then both of them have no p towards n. But then this problem becomes interesting when n is actually prime to p. So 1 and 2 have opposite kind of behavior.
Right. Yeah, okay, that part wasn't obvious to me before, but yeah, thanks for highlighting that. Yeah. I thought 1 and 2 were like thematically similar, but yeah.
No, I think there is a because you know that it is a theorem that in characteristic P, the Milner K theory of fields have no P towards n. And similarly, Galois group also cannot have P towards n. So there is no P towards n. So the part 2 is not at all interesting if n is some power of P. It becomes more interesting if n is prime to P. Then this is not obvious. But part 1 becomes, it has totally opposite role. It's obvious in prime to P case, of course, obvious because of thanks to Mercury-Suslin. And but the main problem is P power, which is very tricky, very tricky.
And is this paper available on the archive already?
Not yet, but hopefully soon.
Soon, yeah.
Yeah.
Okay. Any other questions for the speaker? Questions or comments? I'm sorry, I had another question, which is not exactly mathematical. Is the co-author a PhD student of yours?
Yeah, this will be part of his thesis actually.
Okay.
I think he's attending the talk.
Okay, I
think so.
I think that's, yeah. Okay, yeah. Okay. Any questions, anyone? Well, and also, sorry for asking all the questions myself. How old is this theorem of Fesenko?
Fesenko theorem, I think it is quite old. I cannot tell you exact date, but I would say that it was proven in, if not in 80s, definitely early 90s. I think it was proven in 80s. That he defined some kind of what he calls some topology on the Milner K theory of all higher local fields actually, and using those what he call sequential topology and stuff like that, he had some argument. Using that argument, he could show that kernel rho K. In fact, at that time, as far as I am aware, I think I don't know any other proof of divisibility of kernel of reciprocity for these two local fields except Fesenko's theorem.
So your theorems
we just found surprisingly that we just haven't. We don't use Fesenko theorem in our work at all. It just somehow we directly get this theorem using some more recent cohomological arguments.
Yeah. Are there other classical results like Fesenko's that can be generalized now with the aid of recent developments in
Yes.
optical
For
chromatography?
example, yes. So, for example, actually, Fesenko proved this to be true even for like something called higher dimensional local fields. Then also one knows that this is true. But so one would like to sort of one would like to sort of prove that in a more with more modern way. Another thing is one would like to do is that, which again, my main interest comes from algebraic cycles. So you could ask that you could define some kind of you take some kind of local field and take some smooth projective variety, and then you could take some kind of some suitable motivy cohomology, and then you take its étale realization, and you should ask Fesenko theorem gives you a hint that the kernel might be divisible.
Mm-hmm. But what would divisible mean in
there
that?
is over finite field, actually there is a theorem by what we call Reza Akhtar, where he proves that over finite field something very nice happens. In fact, if you take some sufficiently higher codimension cycles in higher Chow cycles, then they don't exist. And why? Because if you go to the root of the solution, because a well-known fact that finite fields have no Milnor K theory except K1. They all vanish. So, but point is that this does not happen for Milnor K theory of higher fields. So you can't expect Akhtar kind of theorem here, but you could ask that, well, whether it is divisible or the kernel of the realization map is divisible, and that will be the very nice thing to explore. And some of my students are basically studying that.
Does it make sense to ask such kinds of divisibility questions in that level of generality? I mean,
I think in one of my recent papers with my previous graduate students, I did prove such a theorem for smooth projective variety over p-adic field. We actually proved that certain kind of higher Chow groups are divisible plus some finite group. So you expect that if you take codimension to be too high, and you take any higher Chow cycles, then over like nice enough, small enough fields, they should be essentially divisible.
Okay.
For some reason, which I think it's difficult to explain right now.
Yeah, no, it's okay. It's okay. Thank you.
Yes.
Thank you very much. Any other questions? Okay, if there are no other questions, let us take this opportunity to thank the speaker once again.
So I close this, and thank you, Rudrip, for
thank you very much. Thank you very much.
Yeah.